Hi everyone, are you able to hear me clearly and see my screen clearly? Great, great. All right, so should we start? Great. Hi Kamal, hi Abhinav, hi Balaji, hi Bintao, hi Nirav, hi Noor, hi Shahrukh. Welcome to the session. So in the last session, what we have discussed was we were discussing the training models, and we had discussed the normal equation, right? At that point of time, what we understood was that there was a need to learn linear algebra. So some of you had asked that if I could go, I mean, if I could go through the linear algebra quickly, that would be helpful, right? All right, should I go through the linear algebra session quickly? Okay, great, great. All right, so now let's talk about the linear algebra part. So let's start. All right, so I mean, we did a very tiny brief on linear algebra earlier, so we will do it again, and I hope you're going to like it. This time we don't have slides for linear algebra. We'll just go through this notebook, and this notebook is available in the same folder. It is available in the ML machine learning folder on GitHub. You can just pull it in your repository and open it. All right. All right. So what exactly is linear algebra? So we are starting with the um, linear algebra today. So linear algebra is the branch of mathematics that studies the vector spaces and linear transformation between vector spaces. Okay. So in very simple words, when we had to manipulate normal single values, we generally did that. We generally did that. Just give me a second. Let me turn off my phone. Okay. All right. So whenever we had normal singular values, we generally did that using our normal algebra things. But when there were list of things, and we needed to manipulate list of things, that's where the linear algebra started. We all had studied matrices and determinants in our in India, it generally in 11th and 12th classes. Okay, and here Today, what we're going to do is we're going to just do a recap of what those things were and how do we do that using NumPy. Okay, let me just check the audio. All right, looks here this seems to be okay. Let me just okay, so I'm just testing the okay. All right, so is it better now, or do you hear the static in the audio still? Is there a echo? All right. So for us, there is still there is a static, and for others, it's not. So probably maybe Ross, try muting and muting, or see if you could change the device and then change the device back to maybe headphones or something. All right, great. Just try once and all right. So I'm hoping that the audio is clear now. Great, great. So in linear algebra, what we are going to do is today we are going to um, either manipulate the list of values or manipulate list of values, which is generally the matrix. And for that, we did a brief session on NumPy and others. All right. So in machine learning, we rely heavily on linear algebra. So it's very essential to understand what vectors and matrices are and what operations can you perform. Okay. So this is for making sure that the print function is available in both. So, and that's all. All right. So the first thing that we define in linear algebra is the vector. A vector is a quantity that is defined by magnitude and direction. For example, as we talked about the example earlier also, for example, a rocket's velocity is a three-dimensional vector. Okay, the magnitude is the speed of the rocket, the direction, all right, and a vector can be represented by an array of numbers called scalar. Each scalar corresponds to the magnitude of the vector with regards to each dimension. Okay, all right, and each scalar corresponds to the magnitude of the vector. So yeah, so the velocity is basically determined like this, right? So you can see that the velocity of the rocket is three-dimensional vector, the component in each direction. Okay, so this notebook that you see here, you will have to pull again. So you have to go into the console and say git pull. Okay, you have to say git pull again. Okay, and that should do it. So you should say git pull. Yeah. All right. So in case of a rocket, this could be the speed, and so a list of n numbers may also represent coordinates of a point in n-dimensional space. So it's quite frequent to represent vectors as simple points instead of an arrow. Okay, so a vector with one element may be represented as an arrow or a point on axis. A vector with two elements is an arrow or a point on a plane. All right. So the purpose of a vector is we could keep many things in a vector. So vector is essentially list of scalars. Vector is essentially list of scalars. With the vector, either we could represent things in three-dimensional, or um, we could represent, in case of machine learning, list of values such as predictions, list of values such as observations, and so on. So if we are trying to classify videos into three categories like good, spam, or clickbait based on what we know about them, say we have a vector representing the video, like in case of image, right? Like in case of the example we have done earlier about MNIST, the vector represented the pixels of the image, right? So and similarly, on the right hand side, we had a vector representing the value of each, the value of each, uh, the value of each image, the digit that was represented in each image. So vector, you will see as there will be many purposes. So we all have gone through this part. So I hope this is clear. So vector in Python is very simple. So the easiest way of representing a vector in Python is by using the normal list of arrays, normal list, or we call it array. Okay, so let's define X. So here X is our list of values, and okay, so since we plan to do a lot of calculation, we have done a lot of calculation earlier using NumPy. So you should you must have tried the NumPy tutorial earlier. So we could convert any array or list of values into the NumPy array. Okay, because NumPy array is far more faster when we operate on those, while Python's inbuilt list is not that efficient with numbers, because list is very generic, while NumPy's array is a list of numbers. Okay, which is very specific numbers. All right, so we could define a size of vector that can be obtained here. So if you want to access ith element of the vector, we could simply access it. So this is the scalar value at this point. All right, now in order to plot vectors, we will use matplotlib. Okay, so first of all, let's take a look. I'll be sharing these matplot tutorials and other parts very soon. Okay, and this matplotlib inline is something that we need to define in order to display it inside the notebook. Okay, so we are saying import this package as PLT. All right. So now using PLT, we will be plotting things. Okay. So here's a very simple 2D vector, a simple list of 2D vectors. So U and V. Okay. So we have two arrays, two arrays U and V, representing um, a vector having two dimensions. Okay, 2 and 5. All right. I think when we present it visually, then it makes more sense. Now, let's create the coordinates. So the first vector is in x direction, it's 2. In y direction, it's 5. And okay, so we can plot these by extracting 2 and 3 and 5 and 1. Okay, so that's how it is. So first of all, we're going to zip it. Okay, let me just show you what it means by zipping. Okay, let me comment out this piece of code. So what zipping does is, okay, zipping basically brings these elements together. So it will bring 2 and 3 together and 5 and 1 together. Let me show you. Okay, now you see. All right. So does it, okay, what's the best way to print it? Hmm. So I think this will be better. Basically, the idea with respect to zipping is that if you want to bring these two elements together, like 2 and 3 together, 5 and 1 together, then we take two vectors and zip them. And that way we can, like this. You see that? So basically, we created two vectors out of this, two lists or two NumPy arrays. One is 2, 3 and 5, 1. Okay. Now we move next, and this is where here we are basically plotting x coordinate and y coordinate, right? So when we are plotting, what we have to give the scatter function is all of the values of all the points on x-axis and y-axis. So we were separating the x coordinate and y coordinate, all right? And then we are plotting these axes, and that's all. Okay. So you can see that we have basically said from 0 to 9 here and 0 to 6 here. Okay, that's what we did here and plotted these points on the graph. Now, now let's define a function called plot vector 2D. What it does is it plots an arrow. It uses the arrow function to plot. Okay, since we're going to reuse this whole big function again and again, so instead of passing these values again, so we are setting the default values for the array. Okay, arrow, not array. So if we want to plot our vectors u and v like a proper vectors, then we could use the function that we just created like this. All right, so you see that this is a vector. Now, this is u, right? This is u. Sorry, this is u, the red one, and this is blue, the blue one. This is v. So u and v, this is how we are plotting them. All right. Is uh, is everybody okay with it so far? Great, great. Now, in the similar way, we could also plot uh, the vectors having three values, meaning the three-dimensional vectors. And so let's just say define A and B, which are both of them are a three-dimensional vector, right? It has x coordinate, y coordinate, and z coordinate. And in case of machine learning, the vector representation could have more dimension than these. Right now, right now it has only three values, but in let's say the way we studied MNIST, we had 786 dimensions in our vector, which are kind of impossible to plot, right? But we can always visualize it by trimming it down to two dimensions. And that's what we did mostly in case of, say, uh, the California project, whereby we only plotted latitude and longitude. So uh, here we're just trying to plot the three dimensions. And this is what we will also utilize during our understanding of the problem, that we will try to plot things in two dimension or three dimension. Okay, so all right, so this is how you could plot. Say we have these A and B, the A and B. Again, we zip them and extract x coordinate, y coordinate, and z coordinate array out of after zipping. Then we are defining a subplot 3D by using PLT subplot. Okay, and we are saying it's a 3D projection. And then, okay, and then what we are saying here is we're plotting them on scatter, right? So, okay, so here we have just put it 1 and 2. These are the 2 points that it has plotted. Okay, and okay, so it doesn't. Let me just run it. Okay, it's not really required this part. Okay, so there was only 2 points, right? A and B. Okay. Question from Gopi: is it possible to adjust line space for 3D grids as well so that the labels are more clear? I think it should be possible with the sub here while we are defining the subplot. Okay. Good. Now we could also draw the projections in order to see how they're lying in the space. Okay. So this is where we are drawing the projections. Okay, so we have defined our function called plot vector 3D, similar to what we did with plot vector 2D. And here what we're doing is we are, okay, so here essentially what we are doing is we are extracting XYZ from it, and then we are saying XX, YY, and ZZ. All right, basically it is drawing these two lines extra. Okay, it is drawing these two lines extra by so that we can visualize it clearly. Okay, that's what it is doing. All right, so great. So now you can visualize that these are the two points, and right now Now, as we go ahead, we will be using more of these two basic functions of plotting these vectors in 2D and 3D. All right. So the first concept, okay. All right. There are a few more questions. Let me answer those. All right. Let me try to put it on this. Okay. Here. So what we have right now is we have two data points, 2 points A and B. A is at 1, 2, and 8. Okay. So let me show you. A is at 1, 2, and 8, as in A is at 1, 2, and 8. Okay. So this is x-axis, this is y-axis, and this is z-axis. Okay. So it's the y-axis is starting here at okay. Yeah. So y-axis is almost here. This is the 2 probably. Right. Right. So 1, 2, and 8, and the second one is here 5, 6, right? 5, 6, and 3. Yeah. Okay. So basically, these excesses are not starting from the from the from the 0, 0 as usual, but they're starting from the minimal point where our coordinates are. Okay. So if we had some coordinate, something that had right. Just give me a second. Let's say we had one more C here. Okay, and we said numpy array, and we put 0, 0, 0. Okay, and we do the zipping here. Let me first define C. All right. So this is, let's say, 0, 0, 0 in all dimensions. Okay. So this is x-axis, this is y-axis, this is z-axis. Okay. And yes, it is very much possible to plot the XYZ. Now, all right. So let me just pick these few values and zoom it a bit out. Zoom it a bit. Not me. Now you can see that. Okay, both the things together. So these are our three A, B, and C 3 points. Okay, the A is 1, 2, and 8. So A is 1, 2, and 8, while C is 0, 0, 0. So 1, 2, and 8 is this. So it's okay. So here it's 1, 2, and 8. All right. So probably that's why we need to visualize it in the way that projections look really clear like this. Okay. So if I put it like this, it should be good. No, just give me a second. All right. All right. Basically, the putting the projections here makes a lot of difference. And I'm just wondering that. So we have defined this function called plot vector 3D. It takes the it takes the plot as in plot object as argument, so that we can call functions like plot on this object, and then we are passing the 3D vector here. Okay, we are passing these 3D vectors. So we are going over this list, and extracting x, y, z, and we are plotting xx, yy, and zz, right? So here we are saying z is 0, okay, z0 as in the y-axis. So essentially what we are doing is we are trying to plot them on xy plane. We are trying to put their values on xy plane, and that's what we're doing here. So we are okay. So here this is what we are doing. So 0 is the value of z that we are putting everywhere. So we are plotting 2 points, 2 points for all. One is xx as in this here, and other is y and z. Okay. So for each value, we are plotting two values. That's all. Okay. All right. Does options mean all other options like keyword argument? Yes. So if you want to pass, it's not, yeah, this is basically the optional arguments, all of the arguments that we may pass in future. All right. So whatever we pass here extra, that will be given here. Okay. A question from Nirav. Could you print vectors 3D? Okay. So as in this one. All right. Let me just see what it means by V1. Okay. All right. All right. I'm not sure what it means here, but yeah. So yeah. So basically here I'll explain again. So what we're trying to do is for every point, what we're plotting is 2 points. Okay. For every point, let's say we are putting creating 2 points. One is normal xyz, other is x same as x, and other the second one is uh, the third one is with 0 0. Okay. So this is xy0 and this is xy0. So if we had x1 y1 z1, x2 y1 z2, so we would have two more points, x1 y1 0 and x2 y2 0. That's what we are doing here. Okay. This z0 is essentially a 0 value. Okay. So that's what we are doing here, and those are the things that we're trying to plot. Okay. So we are here plotting the dotted line. Okay. All right. Should we move ahead? We are yet to figure out what it means by putting asterisk here. Probably this one maybe here we are combining multiple vectors. Okay, let me just remove it and it should ideally work. I see. When we put this optional argument here, it generally, okay, it can extract 3 values if you put asterisk. Okay. All right. So the other important part that we have been using was the sum of square roots, and that we have used it multiple times. Okay, so that's what is defined as norm of a vector u. Like we basically put four lines around it, two on the left, two on the right. It is a measure of length or the magnitude of u. There are multiple possible norms, but the most common one is the Euclidean norm, right, which is defined like this. So the norm is basically the direction measure of unit, the unit length. So those, okay, let me come back again. So it's the measure of the length. It's not okay. It's the measure of length. How do we convert list of values into something singular value? How do we convert list of values into something singular so that we can compare it easily as scalar? That's the role of a norm, correct? And the same problem we also faced when we were defining our objective function, right? When we were defining our objective function, we had multiple list of values. So figure out, we wanted to figure out what will be the way to quickly measure with a single value, correct? In the case of classification, we did the, we in case of classification, we prepared these numbers f1, f2, and we also uh, basically we prepared that that matrix to just get a singular value out of instead of comparing the full list of value, we basically compare the single value. So basically, in a way that we are trying to convert a big vector into a scalar. And that's what the norm is. There could be multiple kinds of norm, could be summation of magnitudes, as in summation of modulus, modulus as in the mod, summation of the mod. And the easiest one is the Euclidean one. There could be the Manhattan distance kind of thing, and so on. Okay, so then we will talk about the Manhattan quickly after this. Okay, now the the best definition of norm is just square all the vectors, sum it up, sum up all the values, and then do the square root. We could easily implement this in Python, and okay, so you can see that. All right, a question from Gopi: is it better to use to the power 0.5 or np.sqr root? So yeah, I do. Okay, that is something I can check, and maybe we can test. But internally, it is going to use the numpy's power function, and numpy's power function is probably the one that's get called by the square root as well. Okay, so square root is probably calling the same power function internally. Okay, so here we are. So okay, so NumPy also provides a package called linalg, which is linear algebra, and we can use directly the norm function there instead of creating our own function. Okay, so here we created our own function called vector norm, where we went here. What we did was we first of all created a list, right, by iterating over vector, and then summed up that list and did the square root. Okay, so square root is essentially this. All right, so this is what we have. You can see that the norm is probably doing the same thing as what we're doing. All right. Now, okay. So we can draw a circle representing the magnitude of this vector. So the circle is essentially saying that whether this vector was in this dimension here or here, it'll be the same length. Okay. Okay. So you can think of the norm as the radius of the circle if drawn with the origin as the 0, 0 as the origin, and this point, taking this point and moving it around. Okay, so all these points which are lying on the periphery of this circle are going to have the same norm. Okay, all those vectors which are lying on this radius, this circle will have the same norm. Okay, that's what we are trying to show it in the image. All right. Now comes the parts that we have been using so far. We can easily sum up two vectors, u and v. Each value will add with the another value, right? So, so it's pretty straightforward. So we have summed it up. Now, what is the physical significance of summing up two vectors? Okay, what is the physical significance of adding two vectors? Let's take a look. So this is the, all right. So this is something that you can visualize now. Imagine that we have two vectors u and v. Okay, u and v. When we add u and v, this is the resultant vector. Okay, this is the resultant vector. All right. Now, also please note that whether we add u plus v or we add v plus u, we are going to get the same vector. All right. Now, the other way to look at the two vectors is that imagine that blue one is u, blue one is a swimmer, and this is the direction in which the stream is going. Okay, let's say somebody is swimming, and the stream is going in this direction. Okay, so the resultant direction, the final direction of this swimmer is going to be this. Imagine that there is this river, there is a river, and the as in you can actually imagine it like a sea because it's not in a straight direction. So if there is a swimmer who is going in this direction and the stream is flowing in this direction, so the effective direction of this swimmer is going to be this. That's what the vector addition means. Okay, vector addition, that's what vector addition means. Okay. All right. Or you can think of it like you're sitting in a bus, and the bus is going in this direction, okay? And you throw something in this direction, okay? Your effective direction is going to be this. The direction in which the projectile or whatever you threw is going to be in this direction for the person who is standing on the road. All right, that's how you can visualize the addition of the two vectors. Right. So in this diagram, it is very clear that whether you add u with v or v with u, it is always same. And you can, if you take a look at additions, right? Since these two values are going to be added, whether you added this, you put it below this or above this, we are always going to get this value. Okay, so I hope the addition is this clear, the u plus v, the addition of two vectors. All right. A question from Gopi is that what is the impact of origin equals u? Okay, origin equals u. I think origin equals u would be the place where it draws the arrow. Okay, probably that's the one it is. No, actually I got it. So here we are drawing this vector v, okay, this vector v, and we are saying origin is u, meaning this one. Okay, you see this one. So same vector with the origin as u. That's what it means. Similarly, we are drawing this one with origin as v. Correct. That's right. So that's what we are drawing. So starting from this as origin, it's drawing this. This is just for drawing. Wonderful. Wonderful. So these two things that you have to keep track of in most of the operations is commutative and associative. And whenever we are doing operations on vectors, whether in machine learning or whether in distributed computing, these two properties are very much of use. Okay, so like for example, if you want to add list of values or want to find some of the values, you could you could break down the work on multiple machines, right? That's distributing the work. And when you break it down, if the function, the operation is commutative and associative, that means we could distribute and get it done parallelly on multiple machines. Okay, so that's the use in case of the distributed computing, like in case of Spark or big data or things like that. Similarly, here in case of machine learning, you will see that there are quite a few uses of these two properties of any operation. Okay, the these properties, commutative and associative, are of operation like summation, addition, power, or division, or a function, right? The way we define our function, we can say that our function is commutative or it is associative. Okay, commutative means, the way you can remember is, so commutative means in what order, on what order they come. Okay, and okay, uh, basically the commutative means that if a function is commutative, whether you call that function with two arguments, u and v, or you call that function with v and u. Okay, the function should yield the same value. So if you call sum with u comma v, it should give the same result as when you pass v comma u to sum. So basically, when you think of a commutative, you should think of the function that you're defining. Okay, function that you're defining. So let me put it here. So something like this: add v comma u is equal to add of u comma v, right? That means it's commutative. And associative is whether you whether you sum up first two values first, okay, o- or the last two values. Associative means how do you associate? Where do you put the brackets? Where do you put the brackets? Okay, that's what is associative. All right. So these two properties are of very much use in whether matrix multiplication or machine learning. So you will notice that most of the things that we learned in school are of much use in the real computing. Okay, let me just show you the significance of addition. Okay, so when we add something to a scalar all of the values of this, when we add a scalar to a vector, okay? When we add, let's say we have three arrays, T1, T2, and T3, okay? Three vectors, T1, T2, and T3, and we would like to add a value V to all these three, okay? In that case, what does it mean by addition of scalar to the vectors? So this diagram shows you very clearly. So initially these were the three values, v1, I think these were three values, v1, v2, and v3. Sorry, t1, t2, and t3. T1 is, what is t1? 2 and 0.25, 2 and 0.25. This is probably t1, and so on, right? So we had three values. We added scalar v to all of them. It became this. It became this. Or are we adding a vector? No, we are just adding the scalar. No. All right. So we are adding this vector 3 and 4. Okay. All right. So yeah. So when we add a scalar to a vector, what happens is its x and y both coordinates increase, and basically that's equivalent of magnifying. If we are adding a vector to all the coordinates, the shape gets shifted. This is how it would look to you. Okay, so this is a vector, this is a vector, and this is another being same vector being added to all these three points or three vectors here. So eventually, when you add that vector, it basically shifts all these points to another, say here, another place. So basically, it's like shifting the shape. Okay, you can always imagine that the vector was something like a wind, and it blew this shape to another place. Okay, just like when we said u plus v, what does it mean? In the same way, we could also visualize adding one vector to another list of vectors. Yes. So when we are adding, now what happens when we multiply a vector with a scalar? So imagine that we are multiplying 1.5 to 2 and 5. Let's say we have a vector defining 2 and 5. So we are multiplying 1.5 to both of them. So this will become 3 and this will become 7.5. This is right. So if we are adding a scalar to this one, let's say we were adding this instead. So 1.5 will be added to both of them, right? Similarly, when we multiply a scalar to the vector, okay, then we get this. Okay, we basically multiply each individual elements. Now, what does it mean? What does it mean in real life? What it means by multiplying with a scalar a set of vectors. Okay, like this. Okay, so scalar multiplication results in changing the scale of a figure, hence the name scalar. The distance from the origin is also multiplied by the scalar. For example, let's say we are scaling up by a factor k equals 2.5. Okay, so here this is what we are doing. You can see. So we had this initial figure, and we are multiplying it by a scalar. So it is becoming bigger. So now you can imagine that when we are trying to scale up an image, we are most likely going to just use you're going to multiply the image, represent the image like set of vectors, and then multiplying it with the scalar. Okay, so that's what That's what is the significance of multiplication by a scalar in a vector. Okay, so if we divide a vector with a scalar, what happens is it scales it down. Okay, it zooms it out. Does it make sense to you? Let's say we had three vectors, this, and this. These three vectors were represented. And then if we think of these three vectors as forming the shape, forming a two-dimensional shape here, okay? And when we are applying, we are multiplying these all three vectors with a scalar, what happens is the new vectors that are formed kind of forms the similar shape, okay? It basically forms a similar shape, the scaled out version, okay? All right, so the zero vector and unit vector and normalized vector. So zero vector we have already used, we have used the one vector multiple times. And zero vector is essentially a vector full of zeros. Unit vector is vector full of one, okay? Mhm. Sorry, unit vector is something whose modulus or whose uh, norm is equal to 1, meaning if you sum up all the values and do the square root, the resultant will be 1, okay? And the normalized vector normalized vector of any, right? So normalized vector is basically a vector divided by its norm, okay? Its norm. So 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 what you do is normalized vector is nothing but the way we standardized all our values, right? So in the same way we generally compute the normalized vector. So we compute the length or the norm of this vector and then divide each value of the vector with that norm, okay? So that's what it is, and we generally represent it with a hat. Okay, so u hat is equals to u divided by norm of u. Okay, so this is how it will look like. Now I hope this is clear to you. So the normalized vector would point in the same direction as the u, just that it will be of unit distance. You can see this is of one length. Okay. Now, so far we have just learned basics of one. The dot product is something a little bit tricky to understand when it comes to vectors. Okay, so dot product, I mean, it's a little difficult to visualize what it means by dot product. So dot product is nothing but um, for for each value in the vector, okay, we are going to multiply it with another one, and then we are going to sum it up. Okay, so this is how it looks like. So let's just walk through this function. So we are defining our own function called dot product v1 and v2. So we are saying for each here. So we are first of all zipping v1 and v2 so that the values at the same index come together. Okay, then we are iterating over those two values, okay, and multiplying. All right, so this is how it looks like. I'll just show you manually what it means by dot product. So let's say we have u and we have v. That's right, Gopi. It's very much similar to, it's a similar to the matrix multiplication in. So we have U and V. These are U and V. And when we say U dot V, what it means is we're going to say 2 into 3 plus 5 into 1. Okay. Binta's question is, how do you use Markdown to edit text, such as add, dot, bold, etc.? You can actually just click on any of these markdowns and press enter. You'll get a fair idea about it. Okay. So when you just click on enter, and then you'll get it. So this is how you mark down, right? So this is the dot product. So np dot dot is this. So NumPy gives you a function called dot. We will be using this. We use the dot product in the matrix in case of our normalized equation last time, right? Okay. So please note that the asterisk operation will perform the element-wise multiplication, and it is not the dot product. Okay, so here it's going to basically multiply it, but it is not going to sum it, and this the difference between asterisk and dot. Asterisk results in another vector while dot results in a scalar value. Okay. So let's talk about, let's understand the meaning of dot product a bit more. So dot product is commutative, as in whether you say u dot v or you say v dot u, it's going to be same, right? The resulting value is going to be same. The dot product is only defined between two vectors, not between scalar and a vector. So we cannot have u dot v dot w because u dot v is going to result in a scalar, and scalar dot w, which is a vector, does not make any difference. Okay, does not make any sense. The scalar cannot be dot product, cannot do dot product with a vector. Okay. Also, that also means that dot product is not associative. But if one of the values is a scalar, then dot product is basically associative. You see that? So you can say lambda into u dot v. So you could either say lambda into u dot lambda into v. Okay, sorry, lambda into u, then dot v, or you could say u dot lambda into v. Okay, so with respect to the scalar multiplication, it is associative, otherwise it is not. Now there is a property called distributive. Okay, so distributive means the dot product will basically uh, it can be applied over the brackets, right? So that's what it distributed. So let's say you have v plus w, you can do a dot product over these values. Okay, so either you sum it first. If you sum it, either you sum these v and w first and then do a dot product with u, or you do the dot product of individual value and then sum it, you are going to get the same result. Okay, so this property is called distributive. All right, so here we are. So calculating the angle between the two vectors. To calculate the angle between two vectors, we could use this formula. Okay, the dot product between the two vectors u dot v is basically equal to u dot v into cosine of the angle between them. Okay, so in the using the same mechanism, we could find the angle between the two vectors by using by first doing the dot product and then dividing by their individual norm and then taking the inverse of cosine. This is inverse of cosine. Okay, and all right, so one of the many uses of dot product is to calculate the angle between the two non-zero vectors. Looking at the dot product definition, we can deduce the formula. Note that u dot v equals 0. If this u dot v is 0, then the angle is going to be 90 degree between the two. In other words, if the dot product of two non-null vectors is 0, it means they are orthogonal. So u dot v, if it is resulting in 0, that means they are diagonal. They are orthogonal, as in they are perpendicular to each other. Okay, so let's use this formula to calculate the angle between u and v. So we could just define our function called vector angle and say u dot v divided by norm of u and norm of v. Okay, so this is the value of this part, and then we are saying inverse of cosine. So numpy provides us the sine and cos inverse function, and we are using that. Okay, all right. Now, all right. So here we are. Let's just do this. All right. So this is the cosine of theta, right? And if you're saying this, let me just break it down further. Okay. So I'm just wondering what it means by clip. Okay. Okay. So, all right. I think this function is basically making sure that whatever value we are having here should be trimmed to -1 or 1. Okay. But if the value is greater than 1, it's going to bring it down to 1. If it's greater than -1, it's going to bring it down to -1. That's what I think the NP clip does. All right. Is that what you have figured out? All right. So I think this clears it up. So this is what we're doing. We're first computing the the dot product, then dividing by the norm of the two, and then we are computing the inverse of this cos theta. Okay. So yes. So you can see that once we have computed the theta, right? The default value is in radians. Okay, all of the inverse functions, sine inverse, cos inverse, they give the result in the radians, and then you can basically multiply by 180 and divide by pi in order to get the degree. Okay, in the angle. Okay, so this is in radians, then we multiply by 180 and divide by pi in order to get the actual angle. So it's basically 90 degrees. Okay, and let's just experiment a bit on, say, vector angle. Okay, and vector angle of, let's say, two vectors, 1 and 2, and let's say, how can I make it 2 and minus 1, right? This should give a 0, right? No? I'm just trying to define two vectors whose dot product is 0. Okay. Yeah. Okay. So the dot product of these two vectors was 0, so they are orthogonal to each other. Okay. So this is the example of. Okay. All right. I think it did clip. It's just that when we are doing that, it computed in radians. Okay, that's what it did. So 90 degree was that 1.5 something. Oh, we have already written it here. All right. So now there's some good idea called projecting. We'll be using this idea in the sessions later. So we could find the projections on a particular axis using this. Okay. So dot product is also very useful to the first use of dot product was to find angle between two vectors, right? And the so the other use of the dot product could be in finding the projections. So how do you find the projections? You basically do the dot product and multiply by this value after dividing it by the square of the modulus of the vector on which you want to project it on. Okay, so we are projecting here the vector v onto u. So we find their dot product, divide by the square of the norm of the vector which is which is on the on the which is the one where we want to project it, and so on. So let me tell you what it means by projecting. Projecting means uh, if we draw a perpendicular line from U to the V, as in to the beginning to the end of the V, then what will be the size on the U vector? I think the diagram will do it very clear. I'll show you here. Okay, so let's show you this one. Okay, so here this is your U. Okay, we are plotting here. The red one is the U and the blue is V. Okay, so if let's say this is the U vector, this is the V vector. So projecting means finding this distance, finding this vector, finding this vector. That's what is U. Okay, that's what is projecting V on U means. Projecting V on U means this is what it means. Okay, so here what we are doing is we are first of all finding the normalized U. Okay, then we are doing the dot product of U normalized with U. Okay, dot product of U normalized with V, and then we are multiplying it with U normalized. That's what we are doing. So here the same formula is also written like this. All right. So you can see that we have done the square of this one. That means if we divide U by mod of U, as in the norm of U, as well as this by the norm of U, we will get this formula. So we are doing the dot product of V with the unit vector, as in the uh, the normalized vector. So if we are doing V dot normalized vector of U into the normalized vector U, then we'll get the projection. That's what we are doing here. So this is the projection that we have computed, and then we have represented it in the diagram. Okay, so you can see that. Is it clear what it means by projection? This is the projection. Okay, the black one, that's what we are drawing here. Okay, so this is the projection of this onto this. Okay. Okay, a question from Gopi is projection V on U is same as projection U on V? Anybody? Right, it's not, because if you think of it, if we project this V on U, what will happen is we'll draw a perpendicular line from here to here, and that intercept maybe here, maybe it may be a little bit bigger than V, bigger than U, so it will come here. Okay, so the direction of projection is going to be so here the direction of the direction of projection is going to be same as V, and, okay, and so on. All right, is it clear now? Now let's talk about metrics. So matrix is a rectangular array of scalars. Rectangular array of scalars. It has rows and columns, and it is basically the tabular format. Okay, so in case of machine learning, we have used metrics already. We have the data set as the row, the various data points as the rows, while individual features of every data as the columns, right? That was the matrix that we've dealt with. You can think of a matrix as a list of vectors. The previous matrix contains either two horizontal 3D vectors or three vertical 2D vectors. Okay. So either you can think of it like two vectors which are horizontal or three vectors which are vertical. Okay, so matrices are very convenient and very efficient to run operations on many vectors at a time. We'll also see that they are great at representing and performing transformations such as rotation, translation, and scaling. Okay, a lot of image manipulation is nothing but matrix manipulation. Okay, like we want to scale an image, we want to scale, convert it into the gray colors and so on. And all that prisma effect that you have seen are nothing but matrix multiplications under the hood. Not matrix multiplication, matrix manipulations under the hood. Okay, so 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 metrics are quite useful in many ways. The way we studied the normalized form last time, you remember the normalized equation we studied. That's the normalized equation. Uh, we have used the matrix multiplication and other things, dot product and things like that. So though metrics were in use in graphics, in many other mechanisms in computers, the metrics are also of very much use in case of the machine learning. So and since matrix multiplications are very intensive, right? Matrix manipulations are very intensive. Therefore, therefore, a lot of computation is required. Okay. Now, the if you think of two things, if you think of say GPU, right? How many of you have used a GPU or have GPU? Okay, nobody. Okay, so you must be having in the phone in most of the newer laptops, they have the graphics card built in. Okay, now so earlier when people were playing games and the high-end graphics games, people were using the graphics processing in the graphics cards in their computers, right? And in the same way, when you think of new deep learning or machine learning machines, they all have the high-end um, same graphics card, and the reason behind machine learning sharing the same as in same graphics card as the gaming the is the fact that both graphics processing, both graphics processing and machine learning have huge number of matrix manipulation. Okay, so metrics are very useful in manipulating the graphics as well as manipulating the doing the doing lot of machine learning, as in uh, whatever algorithm that we are going to use, whether it's gradient descent or say normalized form, all of those are nothing but matrix manipulations. All right, so that's one important part. Mac Air does not have GPU, and yeah, I think Mac Air has some GPU. So yeah, it has a low-end version of the graphics card, a low-end version of the GPU. Okay, so we all have the graphics card as of today in one form or another. Okay, so yeah, it's a the bigger the matrix it can hold, the more memory it was supposed to have, the GPU. Okay, so So matrix can be represented in Python in many ways. One is the simplest, as in terms of list of lists. So we can define our matrix using this. Okay, and all right. The we are going to use NumPy array. NumPy array by default not only supports the vector but also supports the matrix. And how do we define that? By having the array of arrays. That's all. Okay. So we are going to use the uppercase name for the matrix. Okay. So we're going to use the NumPy arrays to represent the matrix. A question from Noor: can we map a routine to in Python to run only on GPU? So we basically, to run something on GPU, we generally use the GPU specific library in order to do that. Okay. All right. We'll come back to that. Don't worry. We'll go into more details. Okay. Now, so first of all, matrix has a shape, meaning the row and the columns. Okay. And a dot shape means this. Okay. The shape could be as in uh, it could have A cross B cross C, or it could have A cross B. Okay. So number of dimensions right now is 2 and 3 here, like 2 rows and 3 columns. Okay. And the size of A, okay, size of A represents the number of elements in and the array, not the matrix. Okay. And what is this? Second. Okay. So if we have total number of dimensions, if we have, let's say there were 3 dimensions, then we will have 2 comma 3 comma 4, right? Like that. The shape will be then here. Right now the number of dimensions are 2. Okay. The size is still the number of elements, as in the total number of elements in the array here is total 6. Okay. We can always access the elements using any element in the matrix. We could say this is the way we represent generally is the row and column. So this is x11, x12, x13, and so on, right? All right. So this is the general notation. So we're going to use this kind of notation, and the same notation is NumPy's notation as well. So we're going to use Xij. And to access anything in the matrix in NumPy, we're going to use things like that. So if you want to, let's take a look at the actual matrix. Okay. So our matrix is like this. So it has these things. So N12 means this and this. Okay. So the indexing starts at 0 here. So this is 0. This is okay 1. This is 0. This is 1. This is 2. All right. So this is something that we need to keep in mind. So ith row in vector is sometimes notated in. All right. Let's go ahead. So we've already talked about these things. So sometimes we annotate the ith row vector in the matrix as either mi or either m comma star. But again, this is the R kind of a format. Okay. So people often prefer to explicitly define their own names. For example, let xi be ith row vector. So okay, so it won't be too much of confusion. All right. Sure, we will link the two. Okay, so if you want to just take a look at third column, we could say things like A colon comma 2. All right. So what it will do is it will give us the third column, 30 and 60. Okay. All right. So if you want to take the rows, let's say 1 colon 2, as in starting with 1 but less than equal to 2, then we can do this. So this is how we can extract the rows by the range of rows from here. Okay, let me just show you 40, 56, 60. So this will give us the second column, meaning the column at the index 1, row at the index 1, not column. Okay. All right. So if you want to extract, so basically using this kind of notation, we can extract the columns and the rows. Okay. We can extract the columns and the rows. So either each of these values, when we are accessing them, okay, let me reiterate from the beginning what we are doing. Okay. So here. Okay, so this is our A. If you want to just extract this column, what we can do is we could say, give me all the rows and give me the 0th column. Okay, give me all the rows and give me 0th column. I'm going to keep this here so that it's very clear. Now, if you want to say that um, give me the first uh, first row and 2 2 so 1 2, okay, 1 to 2. All right, so now here you can see that I wanted these two elements. So what I've said, give me the first row. If I ask for 0th row, it will give me this one, first row, and elements starting at this index but lesser than the second index. Elements starting at first index and lesser than second index. Okay, so this is how I could access it. Similarly, if I'm only interested in say in these two values, okay, 20 and 50, what will I do is I'll say give me all the rows and give me the first column. Okay, so this is how I can extract list of values from the matrix. All right, is it clear? You'll be able to creatively compose this. No? You can extract the list of values out of this matrix now. Yes. A question from Noor. This has 3 points. So this is a 3 dimension. Three dimension as in the from the vector point of view. Okay. So here it has rows, it has columns, and here it has depth, like something like this. I'll show you. If it has something of this sort, okay, then it would have been, okay, then it would have been the, let me just call it something else. Okay, all right, so this is 3 dimensional. Now you get the idea. So let me also try to format it. Okay, so I think this will give you a clear picture, right? So, so we have this kind of matrix, okay? And can I visualize it in some way? So if let me just see if I could visualize it. So if I have to draw things like this is one table, okay? It has rows and columns. In the similar way, if I had another table, that means it is three. It has this is the third dimension. This was rows and these are columns. Okay? Yes. Okay. Although if you take a look at the individual vector, so you are right in that sense. This we could be saying that if this is one dimension, this is another, then that is three dimension. Okay. But from the matrix point of view, the number of dimensions are counted in this way. Okay. Though Uh, I mean, in our case of machine learning, even though we'll be dealing with thousands of features, we will be representing most of them into a two-dimensional matrix. Okay, two-dimensional matrix. And most of the things that we would operate upon in case of machine learning or anything will be a two-dimensional matrix. Though using two-dimensional matrix, we will be representing the the n-dimensional data. Okay, n-dimensional data. All right, so this is something we did. We learned about indexing, and I hope the indexing is also clear to all. All right. Okay, so the square, triangular, and orthogonal, diagonal, and identity matrix, these are pretty simple. Square matrix means something that has columns and rows, number of columns and number of rows are equal. And upper triangular as in everything on the diagonal and everything below the diagonal is zero. Okay, everything below the diagonal is zero is called upper triangular matrix. And lower triangular is anything above the diagonal towards the right, above diagonal towards the right, this whole thing is zero. That's lower triangular matrix. Triangular matrix is, so triangular matrix is where either lower or upper, they are zero. Okay. And either the lower triangular or upper triangular, they are also called simply triangular. And the diagonal matrix is the one which is having the values only on the diagonal. Okay. The easiest way to create a diagonal matrix is using np.diag, and that way we get a diagonal matrix. You see, from a vector we can quickly prepare a diagonal matrix. Okay. Also using the diag function, we can extract the diagonal of a matrix. Okay. So here we are extracting the diagonal of this matrix. Okay, 159. Identity matrix is very simple. By using np.I, we can create a identity matrix. If we say 3, it'll create a 3 by 3 matrix having all the diagonals as 1. Okay, so if we say 4 here, it's going to create 4 for us. So you can see that. And yeah. All right, just like vectors, we could also add matrix. If you have two matrices Q and R, same size, they can be added together. Okay, the addition is performed element-wise. The result of M by N matrix, uh, okay, will have the sum of each of the elements. So you can see that the values at the same index 1 1 1 1 are added together. Okay. All right, let's take a break now. All right, so I'm back. Should we start now? Great. All right, so I'm back. Should we start now? All right, wonderful, wonderful. Great. So we are learning something really interesting and useful for the entire machine learning course, because we had to, since we were deriving couple of formulas, since we were trying to look at the mathematics underlying, so it was important to learn the basics of linear algebra. Okay, and it was more important to do the linear algebra along with the numpy, so that we get the clarity of the both of them together. All right, so that's why we decided to do linear algebra with numpy today. Okay, so before the break we were talking about the adding of the matrix. If you have two matrices Q and R having the same size m and n, they can be added together easily. Okay, let's take a look. Say we have A is this, and A is this 10, 20, 30, and B is 1, 2, 3, and so on, right? So when we say A plus B, it is 11, 22, 33. Okay, so that's what it is. I hope there is no doubt about it. So addition of two matrices is really simple. Okay, addition of two matrices, since it's basically adding each value with the corresponding value in the other matrix, it is also commutative. It's also commutative. Also, the addition is also associative, as in whether you add B and C first or you add A and B first, you're always going to get the same result. All right. The next one is scalar multiplication. When you multiply a scalar value or a single number to a matrix, what happens? That scalar is multiplied to every element of the matrix. So the scalar multiplication is extremely simple. We basically say lambda m equals lambda into m1, lambda into m21, and so on. All the elements have been multiplied with lambda. Okay, so let's say we had A. Let me just show you A again so that we are all in the same context. So same context, and here A is this. When you multiply this A with 2, this is what we get. Okay, either we multiply 2 into A, or we say A into 2, we get the same result. Okay. All right, so scalar multiplication is commutative and it is associative. If you have two scalars multiplying with the matrix, whether you multiply the two scalars together and then multiply the matrix with the resulting value, or you first multiply with one of the scalars first and then second scalars, right? We're going to get the same result. So scalar multiplication is commutative and associative. Okay, so this makes it very clear. So you have 2 into 3 into 1 and 2 into 3 into 1, as in we first multiplied these two and then. Okay, the result is identical. Okay, it's also distributive, as in if we have two outside the brackets, and when we open the brackets, this will be distributed to both, as in 2 into A and 2 into B. Okay, so it is distributive over addition. Distributive over addition. All right. So scalar multiplication, which is 2 into this, is distributive over the addition of two matrices. All right. Okay. Now comes the matrix multiplication part. So far, matrix operations have been rather intuitive, but multiplying matrix is a bit more involved. A matrix Q of size m and n can be multiplied by a matrix R of size n and q. It is noted simply QR without multiplication sign, dot or asterisk. Okay, so the result P is basically a M and Q matrix. Okay, where each element is computed as the sum of the products. Okay, so I'll explain to you. When we are doing the matrix multiplication, what happens is it's an inverse D kind of way. And okay, so I think I'll do it in more clear way. Okay, let me just go back to my sketch. Okay, imagine that we had one matrix of this form. I'll represent matrix with a rectangle, and we had another matrix with this form. Okay, so all the values from here will be multiplied with all the values from the column. Okay, so it's kind of inverse L kind of scenario. So you take a row, multiply with the column. Okay, so this value get multiplied with this one. This value get multiplied with this one, and so on. So these values, okay, okay. Do you hear some kind of noise in this in the headphones? Yeah, some sort of strange sound is coming. Wow. I think this is something to do with the Zoom. Is it worse now, Gopi? Is anybody unmuted or something? All right. Okay. So basically, we were talking about the matrix multiplication. So we are basically multiplying these values together. All right. Okay. I'm just checking the audio again. I hope things are okay. Is there some other window open for me? Not really. Okay, let's go. Let's go ahead. We'll see to it later. All right. So we were talking about the matrix multiplication. So basically, this is what you do. So you take a row, do a dot product with the column. Okay. You take another row and you then multiply with the column. And that's what you do. Okay. So, so, after doing the dot product of the row with the column, you sum up all the values and put it there. Okay, so this is what is it means. Okay, let me show you with an example, proper example. So here, so 10, 20, 30, okay, so 10, 20, 30, and 2, 11, 23. So the matrix multiplication is here uh, equal to 10 into 20, 11 into 22. Okay, I'll just show you this. So 10 into 2 plus, so this getting multiplied with this, uh, okay, so 10 getting multiplied with 2, okay, this getting multiplied with this, and 20 getting multiplied with 11, 30 getting multiplied with 23, right? So the value is now 10 getting multiplied with 2, 20 getting multiplied with 11, and 30 getting multiplied with 23. Okay, so the value here is 93. Okay, now we'll take this and multiply here. Okay, multiply here. So this, I think I'll just take this example. Okay, all right. So we are multiplying this with this and multiplying this with this, and we are summing up all of it. And when we sum up, this value will be generated. Now we'll take the first row and first column generated 1, 1 here. Then we take 1, comma 1 as in the first element. Then we take first row and second column, it'll generate this. Okay. So when we multiply 10, 20, 30 with 3, 13, 19 as in this and this, then we'll get this second element, and similarly this, and then we'll take another row and do this. So you can see that if this one is 2 by 3 matrix, and this one is how much? What is the size of this matrix? Yes, the shape of this matrix. Anybody? 3 by 4, correct? So 3 by 4, and this one is 2 by, okay, all right. Now, what you see is that this, the number of columns in this matrix, which is 3, should be same as the number of rows in the second one. So number of columns should be equal to number of rows, right? And the resultant matrix has rows equal to this one and columns equal to this one. So the resultant matrix is 2 by 4. Is it clear to everyone? Any questions? Shahrukh, Ross, Prateek, Pavan, Noor, Neerav, Kamal, Gopi, Pintao, Gigi, Balaji, Abhinav. And all right, wonderful. So this is basically the matrix multiplication. All right, this is basically the matrix multiplication. Okay. Okay. Now it's really easy to do the matrix multiplication. You could simply say A dot D. If D is your matrix, this one, it can quickly do this multiplication here. You can simply say A dot D, as in DOT, as in dot A dot dot D. All right. So this way, if you have different shapes, if these dimensions are not matching, if this number of rows in this one is not matching with the number of columns in the first matrix, it is going to give error. Okay. Therefore, therefore, you cannot arbitrarily multiply this matrix. So, so if you do, this was A, right? This was A, this was D. So can we do D dot dot A? Anybody? Is this allowed? Can we do this? Is this valid? No, right? Because the this one has number of rows as 3, while this one has number of columns as 4, while this one has only 2 rows. Therefore, we won't be able to multiply this with this. Okay. All right. So basically, we were able to do A dot D, but we were not able to do D dot A. Therefore, matrix multiplication is not commutative. It's not commutative. Okay. In normal life, we can always do A in as in 2 into 3 and 3 into 2, right? Both are equal, but matrix multiplication is not commutative. Okay. Though matrix multiplication is associative, meaning if QRS and QRS, okay, so basically here, the Q, either we multiply R and S first, and then, okay, then we multiply Q, then we are going to get good results, okay. But, okay, let me repeat what I was saying. So matrix multiplication, even though it is not commutative, meaning A into B is not equal to B into A, okay, A into B and B into A, uh, okay, so it is not commutative, but it is associative. Associative meaning A, as in, if let's say we have three matrices, A, B, Q, R, and S, Q, R, and S. So either we multiply the last two first, okay, and then we multiply Q with that one. It's going to yield the same result. It's going to yield the same result as QRS, okay. Notes question is, can you please give an example of why matrix multiplication is useful? Example in machine learning. Yeah, we'll do that. All right. Now that brings us to a very good point, actually. Okay, let me just take a little diversion. Uh, I mean, little digression. So, okay, all right. So let me explain why machine learning is important. in case of machine. Okay, there were a couple of more questions. Couple of more questions. Let me repeat that. Question from Noor was, what was the extension you use for copying? As in copying the screenshot, or using in the clipboard tracker? I use a clipboard tracker here. It's called jump cut. Okay, it's quite useful. And for copying the screenshot, I use command on my Mac, shift followed by 4 or 3. Okay. Uh, a question from Kamal: what if the columns of the first is not same as row of second? Okay, column. Okay. Yeah, then it's not valid. I think you got it right, Kamal. And Gopi's point is, if columns different is when we do broadcasting, if possible. Okay. Yeah. Question from Gopi was that, okay, point from Gopi was that maybe if the columns are different, then maybe we can do broadcasting. Yes, we can do that. Okay. Okay. Question from Vidya is, the commutative rule should be fine the same size of the matrix. I doubt, because if I'll show you a good question. Let's say we have, say, the kind of two matrix, right? And we have, say, like this. And let's say we are having another matrix. It's just that we have two here, one here, and say 3 here and 2 here, right? So if these matrices are like this, okay, there could be two cases, right? One is we are multiplying like this. So let me first answer this question. It's an important question. So here, what will happen is, let's say when we are, say, multiplying these two and these two, okay, so we're going to multiply these and with this, right? While here, the first column, I think first column will answer the question. So if we think of the matrix in this way, 1 into 2 plus 2 into 3, okay? That is going to be our first element, right? That's going to be our first element. Now, in the same way, if you take a look at here, it's going to be 2 into 1 plus 1 into 2, which are different, right? So even if they are, they are having the same size, correct size, still A into B is not equal to B into A. Very good question. Now, all right. A very important question is that what is the use of matrix multiplication as such in case of machine learning? All right. Now let me take a bit of digression. So when we have, let's say, equations like this, okay, 4, correct, and say, I don't know what it means, but I'm just putting it here. Okay. So okay, I think this will make sense. All right. So let's say we have these two equations to solve. Okay. And we would like to represent it like a matrix. So we can actually represent this like a matrix and then solve it using the matrix instead of using our normal routine. Okay, so we can actually solve these kind of equations by converting them into matrix representation. So the way we have done it earlier in case of our um, example, what we have done is we have represented it like this. We have said 1, 2, these are the coefficients, 1 and -1, right? This is our one of the matrix. So let me just draw something like this. Okay. So here we have 1 and 2, 1 and -1, correct? And the same set of equations could be represented like this. X and Y equals 4 and 1. All right. Now you can see that 1, 2 when multiplied with x, y will become x into 1 plus y into 2 and this. All right. So multiple equations could be represented like matrix, like a matrix multiplication. Okay. In our case, say the linear regression and other things that we are going to discuss, there, there we will represent. Let's say we had some data point on a lot of data point this side, and we have some answer here, and we want to say that the output is a function of input. Okay, in those cases you will see that we will actually do a lot of matrix representation of our data. Okay, but always let's say let me go back here and say that we have okay, let me put it this way. Okay, I think I'll describe it again when we go back to where we deviated from, right? This is where we started our discussion from, correct? So we were trying to do normal equation and then, okay, I'll describe that one once we are after this one, okay? All right. So the important part which we understood was given many equations, we can represent them like a matrix, and then we use the formula for use the various functions and operations on matrix in order to solve our problem. Okay, so that's what was the overall idea. All right, so here we are demonstrating that the multiplication multiplication is distributive, as in if we multiply um, something by something by a matrix, as in if we have q and r, which we are doing the addition of q and r and we want to multiply with s, either we could add them first and then multiply, or we can multiply and then add. Okay, that's distributive. Okay, the product of matrix M by identity matrix results in the same matrix. Okay, this is a very important thing. You will notice it later that more formally, if there is a matrix which is M into N, then whether we multiply M with IN or we do IN into M, we are always going to get the same matrix. Okay, what's the identity matrix? Okay, who can help me with recalling what is identity matrix? Full of ones or only on the diagonals? Only on the diagonals. Okay. Let me show you. Say we have we are defining the okay. So we're defining a matrix of dimension 3 here. It's basically 3 by 3. Okay. So here this is an identity matrix because it has only the diagonals with 1. Okay. And when we say A dot this identity matrix, we would get the same matrix. Okay. Okay, we'll get the same matrix because when we multiply this row with this column, only the first element will be left. When we multiply this row with the second column, only the second element is going to be left. When we take this row and multiply with the third column, only the third element is going to be left. In that way, when we multiply something with an identity matrix, we always get the same matrix. Okay, that's why the identity matrix plays a very important role. Okay. Also, please note that the asterisk operator of numpy is not same as dot operator. It does not perform the dot operator. A dot operation. It basically does the element multiplication. If we are multiplying a with a, it's going to multiply the same element with the element at the same location in the other matrix. Okay. So Python 3 had introduced at infix operator for matrix multiplication, and okay, that you can use. If you're using the version 3.5, then you can use that. Okay, so we are using 3.5 and above, so we can try this one if it works. Did we define these? D is not defined, so we'll have to go up and define D. Where is D? Let's try again. Yeah. So we are able to multiply two matrices A and D. Okay. Now the another important operation is matrix transpose. What is matrix transpose? Converting rows into columns. So 10, 20, 30, which is the row, will become 10, 20, 30 as a column. Then 40, 50, 60 will become a column. That's called matrix transpose. Matrix transpose is basically translating, kind of twisting the matrix across the diagonal. Okay, that's what is the transpose, converting the rows into column. That's far more easier to visualize. Okay, so capital T operation, A dot T transposes a matrix, and this is what we get. So if we do the double transpose, it's obvious that we are going to get the same matrix again. Okay, so there are basically using transpose, we can convert any column into row or row into column. Similarly, we can transpose a matrix, and let's say we had in this equation we had, say, now we want to multiply something with, oh, we have removed that. If we had to multiply this with this column and that was in the row, then we could quickly transpose and multiply. We are going to use transpose extensively later. A question from Bintao: are there two kinds of matrix multiplication, dot product and cross product? Cross product is actually not there. It's just called some product. Dot product is usual. Dot product is the one which we call matrix multiplication, while cross product is not. Okay. So a question from Gopi: in real life, would you use at operator? Is Python 2 going to disappear at any point? So we are not going to adopt to at operator as yet. Okay. until Python 2 completely disappears. Python 3.5 becomes the minimal. So we are not going to use the at operation, okay, as yet. Maybe for next 4 or 5 years. Because we want our code to run on almost on all platforms. Yes, dot T is a function. Dot T is an operator. Dot T is an operator that does this. Okay. It's called T as attribute. Okay. So using the T attribute. So T is kind of attribute defined on that class that contains the transpose of the element. No, small t cannot be used. It is only capital T. Okay, so T is not a function, it's an attribute of this A. Probably for the optimization reasons, they have kept it like an attribute where it basically, maybe it's pre-populating it there or something like that. So it's not a function. Okay, so also if you do the dot multiplication, dot of A and B and do the transpose, it's equivalent to the transpose of the two and then doing the dot. So it's kind of distributive. Transpose is distributive over the dot product. Okay, but it's not really distributive because the order is getting reversed. Okay, and so transposition is distributed over addition, as in if you add two metrics and then transpose, it would yield the same result as addition of two transposes. Okay, so if we take a look at this and we transpose it and then add, we're going to get this. Okay, which is same in both the cases. And if we do the dot multiplication of two metrics and then transpose, okay, we're going to get this. And let's compare it with this. Okay, so here you can see that the here we are saying after transposing, okay, so we are saying D dot A. So we are saying, yeah. So instead of saying A transpose dot D transpose, we are saying D transpose dot A transpose. Okay, these two are equal. So they are not really the distributive, but yeah. Okay. All right, that's right, Gopi. It won't be wise to use capital T to the matrix name. Thank you. Okay, because that'll cause a confusion. Okay. All right. Now, a question is, how do you cross multiply two metrics in Python? Here it provides you, it doesn't, basically dot product does the maximum work. Cross product, I'm not sure if it is there. Okay. Cross product, at most we have something like this. Okay. And since they are of not different shapes, they can't really multiply. Because this asterisk, this multiplication is more like more like addition. Okay, instead of summation, it's just addition. Okay, it's not really a matrix multiplication. Okay, now, yeah, we'll talk about that while later, the cross products and all. Okay, all right. So what does that say, Gopi? The numpy dot cross, what it does? Okay, we'll talk about it as we go ahead, maybe at a later point of time. I'm keeping it as a notes. Okay, all right. So symmetric matrix is the one where the transpose and the matrix are equal. Okay, the transpose of something, if it is equal to the actual matrix, then it's called a symmetric matrix. Okay, the quality of a symmetric matrix is the elements to both the sides of diagonals are equal. So 22 and 22, you can see 22, 22, 27, 27, 36, 36, 49, 49, 0, 0, 2, 2, and so on. So you can see that the the symmetric matrix is the one which has the elements on both sides of the diagonal as same. Okay. All right. So if you want to convert one-dimensional array to two-dimensional arrays in NumPy, okay, okay. So all right. A very common question is how can we convert one-dimensional array into two-dimensional array? So, so we have U, and we can, yeah. So we can use the square brackets around one-dimensional array, and it'll create a two-dimensional array. Okay. So that's how you can convert uh, transpose. Also, please note that transpose only works on the matrix. It does not work on the vector. Okay. So in order to be able to transpose a particular matrix, it must be a two-dimensional one. Therefore, we need to if we need to convert a particular vector into a matrix, we will use this kind of way. Okay, we'll say np array and then put square brackets around this list or this np array. Okay, then we will get a transpose vector. We'll be able to do the transpose here. Okay, let me just see if it is working now. Okay, u is not defined. Okay, yeah, you can see that. So now we are able to do the transpose. There is only one row and that has become the column. All right. The other way, instead of putting square brackets, is asking explicitly numpy for a new axis. Okay, we're just introducing one more axis. In that case, we will also get a two-dimensional array. Okay. Also, the third way of converting a vector into an array is into a matrix is using this format. So, okay, this format. So either of the three, either by doing np.array and you put brackets in here, or we say u and then we in the square brackets we say np.newAxis or we say none. In that case also, we'll get the access. Okay. All right. So this way we can convert it into. All right. From a row vector to column vector, we can also use this kind of a format in order to convert that. All right. So that was about converting a vector into a matrix. Okay. Okay. So we've already plotted the vectors earlier. We can in the same way plot the matrix. Okay. All right. Let me just go back and explain again. Let me go back. Okay. So we talked about here. We were trying to convert single row into multiple rows but single column. That's what we wanted to do, right? So that's not possible if your data is a vector. If your variable is a vector, in that case, no matter, because the transpose of a vector is the vector itself. The transpose of a vector is a vector itself. Therefore, you need to convert that into a matrix because vector doesn't have two dimensions. While we are transposing something, the resulting transposition, we want that to have, um, I mean, for vectors, right? For vectors, all the values are, whether we present it like vertical or the horizontal, it is going to be the same. The vectors have only one axis. Vectors have only one axis, right? So if we are transposing generally means something when you are in, when you have two axes, okay? When you have two axes, only then transpose means something. Therefore, you can't really transpose a vector. You can see that when we say u dot t, we still get the same vector. Therefore, we need to convert a vector into a matrix, right? Now, so this was first method. Then we were able to transpose, as in we were able to convert this row into the column, right? The other way was to use NP axis, as we are saying that we want to introduce a new axis, okay? And okay, and the other format was this. All right, the third format was this, and so on. Okay, I hope this is clear. If you want to introduce axis by in the column way, we could also use this kind of a format. So instead of first converting a vector into a matrix and then transposing, if you want to do both the things together, we could use this kind of a format. Okay, now a question from Gopi: how does it know that whether it's a matrix when you type U and type A? Both are ND arrays, correct? But dimensions, if you take a look, U, right, and A, right, correct? So if you say U dot, let me say print U dot dim, right, U dot ndim, right, and print A dot, okay. So you can see that the difference. The first one is a vector and second one is a matrix. All right. Great. Shape will also be different. That's right. If you try shape, you will get the answer. All right. Great. Great set of questions. All right. So we have already plotted the vectors. Now, the same way we can also plot the matrix. Let's say we have a matrix with two columns and four rows, two rows and four columns, two rows and four columns. Okay. So first of all, we will have to extract the x coordinate and y coordinate from it, and then we'll be able to plot it. Okay. Okay. So let me just keep on doing it because as I go ahead, all right. So we could also plot it in the same way. We could draw the line and plot it in the same way. And okay, we could also fill it like this. Okay, using the polygon and so on. Okay. Now the matrix here, the matrix represents the the rows and the rows and columns of the matrix represent these points. Okay, represent these points. These are how many points? 3 plus 3 is 2 plus 2. Okay, 6 points. No, this for 4 points only. Okay, it is having 4 points. Where are those 4 points? These 4 points, right? 1, 2, 3, 4. I'm just wondering what happened to the other points. It's supposed to have 8 points. Okay, no, these 4 points only. This is X, this is Y, this is, sorry, this is first point, this is second point, this is third point, and so on. Right? Let me just pay a little more attention. 3 and 0.2, that's correct. 4 and 3.5, that's correct. And so on. Yeah. So these are x coordinates and these are y coordinates. So 3 and 0.2, 3 and 0.2, 4 and 3.5, 4 and 3.5, and 1 and 2. Okay, so this is what we have. We can draw them with the dashes and we can fill it. Okay, so that was the simplest way of representing those four coordinates. Those four coordinates. Okay, this is a closed area that we have colored above. Now, we saw earlier that whenever we do vector additions, it results in geometric translation. So vector multiplication by a scalar results in rescaling. Remember, whenever we multiply a scalar and so on, basically does zoom in, zoom out, right? And vector product resulted in projecting a vector onto another, rescaling, measuring the resulting coordinate, right? So the way most of these operations were helpful in case of vectors, in the same way, those same uh, operations are very helpful in case of matrix also. Okay, so there are many geometric applications of of matrix manipulations, matrix operations. There are many geometric as well as machine learning applications of the matrix operations. Okay. Okay, let's take a look at what it means by adding two matrices. Okay, let's take a look at, let's say there was a second matrix that was represented as H. Okay, these are the various vectors that were represented as separate matrix, and the P was matrix. P was kind of P was kind of P was another matrix. So there we have, let's say we have two matrices, H and P. Okay, what is H? H is set of vectors, and P is a matrix represented like a shape. So when we say P and H, it basically moves all the corners. Okay, it's as if that let's say there are four people. That these four people have moved the four corners of the shape. Okay, so whenever we are doing the addition, the way when we added something to scalar or vector, right? When we added two vectors, so the idea was that you are moving and you're pushed by the air, or you're pushed by the stream. You're swimming and the stream pushes you. In the same way, if the matrix is represented like a shape and we are adding another set of vectors to it, or we are basically adding another matrix to it, this shape will be moved by the another set of another matrix. So while another matrix is represented like a set of vectors, okay, and this matrix is represented like a shape. Okay, we could do the inverse also. We could represent the other matrix as the shape and our current matrix as vector, and still the resultant will be similar. Okay, a question from notes. So one more row would result in z-axis. One more row would result in z-axis. Correct, correct. All right. What is add art is doing? Basically, it's adding the polygon to the picture. Okay. All right, so this is what is happening. So this is the significance of the addition. Okay, and you can see that we have added the same vector and it just moved the figure from one point to another. Okay, so if we have a list of same vector, so if we do scalar multiplication to a shape represented by a matrix, it basically scale it out. You can see that. So you can now understand that when we say zoom in, zoom out on a picture, the picture is nothing but pixels, a matrix of pixels, right? The you can say that it's a matrix of the pixels. And what is a pixel? The intensity of each point, correct? So that's our picture, our photo, and we want to scale it. Then what we do is we basically zoom it out. All right, so that's basically the geometric application of the geometric application of the multiplying with a scalar. Okay, so for zooming out we just multiply, and for zooming in, as in uh, shrinking the photo, we just divide it by the scalar. Okay, now we talked about projections on an axis. So projection on axis is something really simple. Okay, I'll show you. Okay, projection is more like a shadow. All right, so let's say we have U and P. Okay, what is P here? P is, so we have P and we have U. Okay, we have two matrices, P and U. U is just a simple matrix with kind of a single vector. Okay, what did we do here? Okay, here. So this is our matrix. Okay, P is our matrix, 3, 4, 1, and this. And U is our another matrix with single value. Okay, single row, single column, and it has only 1 and 0. If we said U dot P, what happens in case of U dot P? Basically, it has single column, two values, two rows, single column. That's what it is. Right? No, it's a single row, two columns. Single row, two columns. So when we are, that's why we are able to do U dot P, 1 multiplied by 3, 0 multiplied with dot 2, and so on. So it'll result in only first column, like 3, 4, 1, and 4.6. These are the horizontal coordinates of the vectors in P. In other words, we just projected P onto the horizontal axis. All right. So let's say if you want to find out where does this corner, how does this corner meet this particular axis, then we generally do the projection. Okay. Let me just, yeah. Okay. All right. Let's say we have another vector or another matrix that's represented like a vector. So here, let's say this is our line that is represented by this particular vector. Okay. So if we do a projection, of this vector onto, if we project our P onto this is how it's going to look like. Okay. So we can actually project on any other axis by just replacing U with any unit vector. For example, let's project on the axis that 30° above. So we are able to quickly find the point where this is meeting. Okay, where this is meeting. So at number of places, like the way we are doing in case of you remember our discussion in classification where we were trying to find the loss, correct? So there, what we were doing is we were trying to find the distance of any point from the line, correct? In those cases, we could generally project any vector or any matrix onto a line and then find out where it's meeting and then find out the distance between the two quickly. Okay, so those are the ways, those are the places where the matrix multiplication or dot product will be used extensively. Okay, so we can quickly find where, if we drop a perpendicular line or a vertical line from here to here, where would it meet? If you want to find that out, we could simply do a dot product with the unit vector of this one. Okay, that's the purpose of dot product generally. Okay, if you want to say do the, let me just see where we are. The other use case of matrix multiplication is to to do the rotation. Okay, so let's say we have a matrix containing various angles. Okay, and we would do the dot product of this matrix, then we'll be able to kind of rotate it. Let me show you a diagram. Okay. All right. So let's say we have set of vectors represented as a matrix, and when we multiply this matrix of vectors with this matrix of our points, so this matrix is basically represented like a vector, while this matrix we have represented like a shape. So when we do the dot product, this point is going to be moved to this, correct? and this point is going to be moved to this, right? This point is going to be moved here, this point is going to be moved here, and so on. And that way, it's kind of a rotation here. It's kind of a rotation here, because if you see this line, we are projecting this point onto this line. Similarly, if you look at this unit vector, we're projecting this onto this. We're projecting this onto this, and this projecting this onto this. And essentially, it is, if you look at your matrix like a shape, it's essentially rotating the matrix, rotating your shape, rotating this shape to the new place. Okay, if there was all of these vectors were of the same were same identical matrix, as in they all were on equal angles, then we could actually move them equally. It'll basically this is what is causing the matrix rotation. How should I explain this? Let me go back and try explaining again. Let me go stepwise here. Okay, let's take a look at this. So we are saying that we have four angles for each of the four corners. One is 30-degree, other is uh, one is okay. So we created the two unit vectors that make 30-degree and 120-degree with the horizontal axis. So instead of we computing the value here, what we have done is we have found the angle, and the horizontal projection and x and y projection is what we have defined as the values here. Okay. Now we are saying that we have created a matrix out of it. Okay. So these basically x-intercept, y-intercept, and so on. So this V contains the dots or contains the vectors at those angles. Okay, right? And yes, okay. Once we do that, we can do V dot P, meaning project P onto V. Okay, so the first row equals to V. Okay, this is clear to all of it, right? It's a standard one. Okay, so first row is equal to V1 asterisk with P, which is the coordinate of projection of P onto 30-degree axis. Okay, so basically here, if you take a look at it, this one, right? So we are saying this multiplied by this. Okay, so whatever is the angle this one is forming, on that angle this projection is going to be there. Let me, can I just keep both of them in the same screen? Yeah. Okay, I think I'll just describe this part, and then rest of the part you can figure out. Okay, I will be back to the machine learning afterwards. Okay, so basically what we are doing here is we have defined four vectors. Okay, we've defined four vectors, and we are basically projecting the shape onto those angles. Okay, that's all. That's all is the significance here. So the important part is that a lot of transformations, lot of image transformations, lot of data set of transformations can be done using the matrix multiplications or matrix operations. Okay, here is another example. Okay, here is another example. All right, so we've just moved a shape into another dimension. Okay, I think we can continue from here. All right. So you can take a look at this one. There are some more things here which you can take a look. And I think this much knowledge is good enough for understanding the rest of machine learning. Okay. A question from Gopi. I should have asked this earlier, but it just came to me. How is that polygon plotted with 4xy coordinate as two triangles? Correct. So yeah, I'll describe. Let me, yeah, good question. So what it had done is like this, right? This is the these are the fourth coordinates. Okay, these are the four coordinates, 3 and 4. This is the 3 and 4. 3 and point 2. This is 3 and point 2. Then this is 4 and 3.5. Correct. And then so what it has done is, okay, yeah, I think this will make more sense to you. So what it has done is 3 and 4.5, right? This is 3 and 4, 3 and point 2, 4 and 3.5, 4 and 3.5, correct? And then 1 and 2, okay? Then 1 and 2, okay? This is 1 and 2. And then 4.6 and 2.5, 4.6 and 2.5, okay? So that's how it is done, and it's basically in that order. Okay, so when we draw it like this, and then last one it has joined it back to the first one. So if you see, it has become like a shape. It has become like a shape. This is one shape. Okay. Important to notice is even if we represented it like a square, it will still make the, it will still look the similar way. Okay. And all of these things will still remain valid. Okay. In whatever order we plan them out. All right. So, all right. So matrix multiplication and matrix operations are of huge use, not only in geometric translation, but also in the machine learning cases. We will go into, after this, we will continue with what we have learned here. Okay. Then this will make a lot of sense now to you, like transpose and inverse. Okay. Inverse, I'll describe inverse quickly after this. Okay. All right, so we'll continue from here tomorrow. I think this session was all about linear algebra, and I was hoping it to be of 1.5 hours, but it turned out to be full 3 hours. Okay, a question from Binta. Could you have a link to NumPy tutorial and confirm the deadline of the end project? Sure, sure. So end-to-end project was kind of 2 weeks. Okay, 2 weeks from the date of your start. And I was assuming the date of start to be last Monday. Okay, so you have one more week to finish. All right. So by next Monday, it would be you should finish at least one end-to-end project. Okay. All right. Thank you, Gopi. I hope this session was useful. This was not as per the plans, but okay. All right. So thank you, everyone. Thank you, Balaji. Thank you, Bintao. Thank you, Gigi. Thank you, Gopi. Thank you, Kamal. Thank you, Nirav. Thank you, Noor, Pratik, Shahrukh. Okay. A question from Gigi was, where can I get one-on-one? Okay, I'll just, you just book this one-on-one session using the same link, and okay, that will be better. And okay, let me catch up with you, Gigi, after the session. Can you just stay back and then we can discuss? Okay. Okay. All right. So Noor has got a collaborative today. So those, I think most of you are starting the project today. Do you want 2 weeks from now? Somebody else has also messaged me. Okay. Okay. So you can take 2 weeks from now. Okay. 2 weeks from today, as in, meaning, so which will be, what will it be? It'll be 14 plus 20, which is 30, 34, which is 3rd of Jan. Okay. So yeah. So we can keep 3rd of Jan as the end of date, right? 3rd of Feb, not 3rd of Jan. 3rd of Feb. Okay. Okay. So Pratik will be helping you with the setup. Okay. Pratik will be helping you, Bintao, with the setup. All right. Okay. So yeah. So you can just send an email to reach us and he will help you. He's in the session itself, so he'll respond to you. Okay. Okay. And okay. So yeah. All right. And okay, I'm just making notes. Yeah. Okay. So all right. Great. So I look forward to see you tomorrow. I look forward to see you tomorrow and have a good day.